All right. So welcome to this live stream of Engineering Trainer TV. My name is Luuk. I'm the CEO and one of the founders at engineeringtrainer.com. And today we will have a conversation with Neil Parkinson, who is a consultant and instructor for pipework failure prevention, with roughly 4 decades of experience with vibrating piping systems and structural integrity of structures. And this live stream is related to one of the upcoming courses that he will be teaching on engineeringtrainer.com called Pipework Vibration Training. So if you really want to become fully knowledgeable about this topic, make sure to review that course. The link is in the description of this live stream. Well, Neil, it's a pleasure to have you on board. How is your day going so far?
Well, hi Luuk. The day's going well, thank you. Yeah, thanks for inviting me. I'm looking forward to this.
Awesome. Happy to have you. So next to Neil, I also want to welcome everybody who is watching this stream. I want to invite everybody to join the chat, of course. Make sure to ask questions, provide comments, join the conversation. And as always, I want all of you to share from where in the world you are tuned in, right in the chat. So let me just kick that off myself. Right, there we go. So I'm tuning in from Utrecht, the Netherlands. Make sure to share from where in the world you are joining us. If this content is relevant for you, consider subscribing to the YouTube channel and make sure to follow us on LinkedIn as well, which is our main outlet. And of course, connect with Neil and myself on LinkedIn if you want to start a conversation. The aim is to take roughly 30 minutes for this live stream. We might extend a little bit longer if we have a lot of questions. Having said all of that, Neil, from where are you joining us at the moment?
Well, I'm near Manchester in the UK, a little place called Bramhall, just south of Manchester.
All right. So we are not too far away when it comes to time zones. I'm looking forward to see where all the viewers are from. Now, before we before we dive into the slides, Neil, maybe you can kick off by telling us a little bit more about yourself and your career.
Okay. Well, I'm basically a mechanical engineer. I'm a fellow of the Institution of Mechanical Engineering, and I've been working in engineering for nearly 40 years. For 34 years, I was working for a consultancy called AVT Reliability. They were based near Manchester,
right?
Where I was the technical director, and I also ran the asset integrity division. And it was there that we developed all our skills and knowledge and solutions for identifying and solving pipework vibration problems. And then in 2012, in parallel with working for AVT Reliability, I started my own company, VibTech, to focus on the training side. So I've been running training courses around the world for engineers, trying to share with them what good practice looks like, what they should be doing and what they shouldn't be doing, how to solve issues. So that's my main focus now, is just on pipework vibration. Everything I do is linked to pipework vibration, either training or consultancy.
All right. Awesome. So thanks for sharing. Let me just grab a second to share the slides. Yeah. All right. So the slides are shared now, Neil.
Okay.
Yeah, I invite you to kick things off.
Okay. So what I thought would be an interesting thing for us to do on this first session is to talk about the mistakes that are most common. In other words, where people are not applying best practice in terms of pipework vibration avoidance. So we'll talk about these 6 that I've identified. But before we do that, I should first of all just say a thank you to the Energy Institute. All of the information about pipework vibration best practice comes from an Energy Institute publication, which I will show you in a minute. But a lot of the slides I've used today use photographs from the Energy Institute. So I do have permission for that. So I just want to say a thank you to them.
Nice.
And then also just to define what I'm talking about here. So I keep saying best practice. Well, what I mean is if operators apply these best practice guidelines, they will minimize the risk of vibration-induced fatigue failures in the pipework. That is vibration that can cause a crack from the pipe from which you can have a leak of gas or liquid, which could be extremely dangerous for a petrochemical or chemical site. So that's what we're trying to do. We're trying to avoid cracks in pipework that are caused fundamentally by vibration.
Is there, just to jump in with a question, like is there a clear distinction between high cycle and low cycle fatigue and the associated loads?
The guidelines cover both. So some of the damage that's done by fatigue is always caused by a combination of different amplitude, different frequency vibrations. So it could be a one-off transient event, for example, due to surge or due to slugging or due to a valve closure that causes some large stresses, but it doesn't happen very often. Or it could be that it's almost continuous vibration of a low amplitude, but can still cause damage. And whichever of those causes the most damage, you can't always say without doing proper monitoring, but they both can be damaging, and the guidelines cover both cases. Just some of the terminology which might be useful to us when we're talking about pipework vibration is this. So this is an example of a small bore connection, okay, connected to a main line. So the main line typically would be anything from 2-inch to 36-inch. I apologize for using inches. I know we went metric in this country many decades ago, but you know what I mean. The small bore
I think most are still used to inches when it comes to diameter.
It's not just me then. So when we've got a branch connection, so sometimes we abbreviate this to SBC. As it says, SBC is our small bore connection, sometimes called a small branch connection. Okay, but that by definition is something between 1/2 inch and 2-inch in branch diameter. Okay, and this is where most of the failures will occur in pipework vibration. It's not the main lines themselves that are failing, it's these welded connections between the small bore connection and the main line.
Right.
This picture shows it perhaps a bit more clearly. So we've got the small bore connection, and it normally has a fitting of some type. So a welderlet fitting would be a very common one. You'll hear that term a lot, but it could be a threadolet, a sockerlet, a Nippon flange, and there's lots of different types. But it's got a welded connection with some type of fitting, and it's connected to a number of valves. So it's got mass. It's like a cantilever. It's got a large mass supported just by that small diameter pipe.
Yeah.
Okay. Now here's a picture. I'm going to run this video in a second, but this is a motion amplification video, which is very good for explaining the problem. This has been amplified. Motion amplification is a video technique where you can record a video where you can't see any movement, then you can amplify that movement and then replay the video, showing it sort of with a greater visualization.
Oh, wow.
And so if I just turn off my laser pointer for a second and run this video, you'll see this small bore connection now moving from side to side and leaking because it's a fatigue crack at that weld. But the interesting thing is that everything on this image is being amplified by the same amount. So the main line vibration is also amplified, and even then you can't see it.
Yeah.
And that's an important point, because some people think pipework vibration only happens when you've got really extreme levels of vibration, and as such they assume it's probably visual. You could visibly see the vibration, where in fact you can't. Even when it's amplified, you can't always see it. These are small levels of vibration that happen in normal processes. So we're not talking about fault conditions necessarily, although it might make it worse, but normal levels of vibration caused by the flow of fluid through your pipes, caused by the type of machinery that's driving that fluid, caused by the operation of valves. They can cause vibrations of the main line. Okay, always of the main line. They don't excite the small bore directly.
Yeah, in this particular case, could you maybe like would you be able to see the vibration of the small bore
No,
connection with the
no,
eye?
that'd be totally invisible.
Oh,
If you
really?
put your hand on it, you would feel some vibration, but you wouldn't see anything at all. You'd need a
Oh, that's
vibration
tricky.
meter to quantify the vibration, but that's why motion amplification is such a great technique.
Yeah.
Okay, so these small levels of vibration are caused by normal process conditions which excite the main line, and it's the main line vibration that's causing the small bore to vibrate.
Yeah.
Okay, so and it's done it in a way that it's now been amplified by resonance of the small bore connection.
Yeah. I mean, from a geometrical point of view, it looks like let's say a stiff point, which is the header, then a spring with a certain amount of flexibility, and then a weight, which is determining the frequency, the resonance frequency, I guess.
Yeah,
Yeah.
it is just like a cantilevered mass. It is
Yeah.
exactly
Exactly. Yeah.
what it looks like, with the highest displacement at the top in this case,
Yeah.
and the highest stresses at the welded connections. So what happens is, over time, this vibration causes movement, which causes cyclic stresses at these welds. And of course, the welds are also stress concentrations. Then we can get damaging stress levels in these welds, which over time can lead to a fatigue crack. And that crack doesn't happen instantaneously. It will grow over a period of time until it becomes a through wall crack where we can
Yeah.
see a leak, as you can in this video. So
But I think
that's
that the number of cycles is relatively high. I mean, I'm not sure what the frequency of this particular video is, but let's say it's a few hertz or something.
yeah.
It
Well,
adds up.
typically for problem levels of vibration, you're normally looking at frequencies of less than 100 hertz and often less
Right.
than 50 hertz.
Yeah.
Okay, so they are relatively low frequency, but over time you still can build up millions of cycles, of course.
Yeah. Exactly. Yeah.
Okay, so let's just move on to the next slide. So we can actually now start looking at the 6 most common mistakes that I think people make. Okay. We're going to go through them anyway, but I'll just summarize them quickly. So it's people that don't have any consideration for vibration at the design stage. People who have perhaps implemented some measures to stop vibration, but they haven't done it properly. They haven't used industry best practice as covered in the Energy Institute guidelines. I normally just abbreviate them to EI guidelines. Okay, that's what that means. And that can often lead to a case where we've got pipework which has poor resistance to vibration. In other cases, we see lots of examples of people who have tried to solve problems by putting braces onto small bore connections, because that's where most of the failures would occur. And they've done it in a way that's either ineffective or it's actually made it worse. So it's causing more damage than if it didn't have the brace at all. And then remembering that the small bore connection is only excited by vibration of the main line, then the main line is also important here, how well supported that main line is. That's often a big contributing factor.
Yeah.
So let's look at those one by one. And if you've got, just shout out, Luuk, if you've got any questions. But
Sure.
in this first example here, I'll just zoom in quickly just so you can see what I'm talking about. We've got a pipe. It's insulated, so you can see it's got lagging on it, but it's a pipe and it's supported by a hanger rod from a spring hanger. This is like a box with springs in that will compress the springs due to the weight of the pipe. And that's mounted onto a cantilevered horizontal beam, which is attached to this vertical post. Okay, now this is an example of a pipe support that's not been designed to have any vibration resistance at all.
Yeah.
Okay. It's only designed, by default, pipework is designed to carry the weight of the pipe, okay, and to allow for thermal expansion of the pipe if it sees high or low temperatures. So because the weight of the pipe is caused by gravity, that always acts vertically. And so often we'll see pipe supports are stiffest, they have the maximum stiffness in the vertical direction.
Yeah.
And they're often quite unstiff. they're flexible in the side-to-side horizontal directions.
Right. Yeah.
And you can see that in this case, this spring hanger has got virtually no stiffness. It's a spring. Okay. If you wanted your pipework to vibrate, you would mount it on springs. This is
Use a spring.
exactly the
Yeah.
wrong thing to do.
Yeah.
But it's got enough. It's got enough load-bearing capacity. It can carry the weight of the pipe, but it hasn't got the stiffness to stop movement of the pipe. If this pipe wanted to vibrate vertically, the spring hanger would allow it. If it wanted to vibrate side to side, this hanger would allow it. This whole post would move side to side as well. The post, this vertical post, it's got no diagonal stiffness. There's nothing to give it any side to side stiffness.
Yeah. It can
And
be a tricky
it's
situation
common.
though, right? If you have a lot of thermal expansion and you need to have different load cases or like processing conditions and have the vertical loads organized correctly, that's typically why you want to explore using hangers. Yeah, so it can be tricky, right? Not sure like what could be a good.
Well, it's right. You can't just put a fixed support everywhere.
Yeah.
You've got to allow that thermal expansion without over-constraining your pipework. And in fact, that would be a good subject, Luke, for another one of these talks where we could talk about common solutions. But the solution in that case,
I agree. Yeah.
the best solution are to use viscoelastic dampers, okay, which don't carry any static load at all. They only provide a reactive force proportional to velocity of the pipe. So it is a true damper.
Yeah.
So if you fit those alongside an existing spring support, the spring will carry the weight of the pipe, and the visco damper will stop movement of the pipe.
Yeah.
But it'll also allow thermal expansion.
Right.
In any direction. So they don't constrain the pipe at all statically, but they do for dynamic loads. So that's so what else have we got here then? So if there are if there's no causes for vibration, so there's no flow-induced vibration, flow-induced pulsation, that's what these letters stand for, acoustic-induced vibration, surge, momentum change, then this will be perfectly fine. And by default, most of your pipework will be fine. The problems you'll only find normally once it's a new plant, it's been commissioned, it's after commissioning, you'll know if you've got a vibration problem or not, because you'll find some sections of pipework are now vibrating. And it makes sense, because if you try to design your pipework so that every pipe support was it was a dynamic support, it would have to be an awful lot more substantial.
Yeah.
It would have to limit movement rather than just carry load, which is a totally different concept.
Yeah.
As a rule of thumb, we want to limit movements to less than 0.1 millimeter for whatever load is applied to them. That's a sort of rule of thumb stiffness that we're looking for. Okay, so that's the first mistake people make then, is for a pipe that is excited by something, it hasn't got resistance to vibration built in at the design stage. And that's why most vibration solutions tend to be retrofit solutions, because you only find out about the problems afterwards. It's too late to go and change the pipe size or change the pipe wall thickness.
Yeah, but it's tricky, right? To during design stage, and I know we'll get into that as well. But it can be difficult to like find those locations.
No,
in
fact,
advance, right?
No, because if you look at what's in the Energy Institute guidelines, so this is what it looks like. If I just move this across, you can see the title: Guidelines for the Avoidance of Vibration-Induced Fatigue Failure in Process Pipework. This is the current edition, the second edition. It was published in 2008, and it's due to be updated hopefully later this year.
All right.
But within this publication, it covers lots of different things. And actually, the first part of this is a technique called quantitative assessment. And this actually lets you calculate a risk factor for every section of your pipework at the design stage, which will give it a score. It's called a likelihood of failure factor, the LOF. And the higher the score, the higher the risk of vibration problems. And so if you did these calculations at the right stage, you could identify in advance which sections of pipework are more likely to have a problem.
Yeah.
Okay, so and you do that for each of 6 common excitation mechanisms. So flow-induced vibration being one that most people have heard of. But there are others as well. And you can also use the same technique to assess the risk to your small bore connections and to thermal wells as well, actually, which are intrusive within the pipe. But that's an important part of what's in the Energy Institute guidelines, this ability to assess the risk. And it's also good for diagnostics. If you've got a pipe that's vibrating, you know something must be causing it, but you might not know what. But by doing these calculations, hopefully one of those excitations will give it a high score. For example, flow-induced vibration. You can say, yes, it definitely looks like it's flow-induced vibration because we've got a high score for that calculation. So it's confirmation. But it also tells you what to look for with a visual inspection. Just by walking around your site, if you know what to look for, you can identify good and bad practice or pipework that's more at risk. Okay, and so there are lots of photographs in there showing good examples and bad examples.
Right.
And then, because we're talking about vibration, obviously there are techniques there for how to measure the vibration. Let me put my laser pointer on again. How to measure the vibration and how to assess what that actually means. What's an acceptable level of vibration for our pipework? That's all covered in the guidelines. And then, if you've got a problem, you want to assess it further. Okay, just because the vibration's high, you may still be okay. You have to assess it further using some specialist techniques. And they might be things like finite element analysis being a very common one. You might want to do some modeling to try and predict the behavior of pipework and look at how can I improve it? If I put an extra support here, is it going to have the effect I want it to have? That sort of thing. And also it tells you, if you have got a problem with vibration, what are the common corrective actions? What should you be doing to fix it? And this is a good...
Are these likelihood of failure assessments common these days during, let's say, design stages for let's say, every meter of pipe?
Some of them are. So routinely, I've been involved in lots of new build projects in the Middle East, and routinely they'll do flow-induced vibration assessment and they'll do an acoustic-induced vibration assessment. But that's all they'll do. And they'll do that at the feed stage. So but for lots of existing plant, it might never have been done.
Yeah. And
also the failures don't happen straight away. I've worked on sites where after 8 years of operation, they were suddenly having failures. They say suddenly that these cracks have been growing for the last 8 years, but they were saying they're suddenly starting to fail. All these small bore connections were failing. So what else have we got here? We've got the corrective actions, yes, and then we've got it's got a summary of what is good practice, basically. That's all in this document. So it's a very, very powerful document. But I would hold off buying it because the third edition is due out very soon. So that's the thing that people do wrong. They're not fully aware of this document, even though it's been around nearly 15 years, and they don't apply all the sections of it. They might just apply, for example, just the vibration monitoring. People like to measure vibration, look on a chart and say, yes, it's good or it's bad. And people generally don't like doing lots of calculations. And so they try to avoid that bit as much as possible. Whereas you can use software that makes that very, very simple to do those calculations. It shouldn't be something, it is a powerful tool. We shouldn't avoid using it. Okay, so that was the second of the 6 most common mistakes. The next thing I see a lot of is pipework which has low resistance to vibration, which might not matter if there's no cause. There's got to be a root cause of the vibration, hasn't there? There's got to be something that causes it. So it may be that during normal operation, if I measured vibration on one of these small bore connections, so there's one here, and there's another example here, they might be perfectly okay. If I put a vibration meter on, the vibration might be acceptable. But every time you close a fast closing valve, this thing might see a lot of vibration. And that's what Luuk was saying at the start. It could be that it's seeing this low cycle fatigue. So every few days or weeks, it sees some high stresses, which over time can still lead to a failure because it's got low resistance to vibration, which means it's vulnerable to transient events.
Yeah, it's very it clearly looks like very like top heavy section of piping. I mean, you have this really small bore branch, and then these thick flanges and thick valves. Like it's really hard to avoid having coming up with a piping geometry or routing that solves the issue with such a high mass of the valves compared to the thickness of the piping.
Well, it can be difficult, and I think a lot of people get put off by complex geometry by thinking, well, if I had to try and design a brace to fix, because some of them, these are quite simple compared to some of the ones you might see, it is going to be off-putting. But in actual fact, I'll show you a bit later on some examples of a very easy off-the-shelf solution where with just 2 dimensions, you can order some bracing that would fit any small bore connection. And you buy it as a kit, you fit it yourself. So it's actually very easy. Another thing I should say about these is the vulnerability, we can calculate that using this quantitative assessment tool that's in the EI guidelines.
The likelihood of failure.
Yeah, the likelihood of failure.
Yeah.
And it uses a number of factors, but what it doesn't use is how many bends there are in this. Whereas the bends are actually quite important. This one on the right has got a single bend, whereas this one on the left has got 2 bends. It's got a bend that I'm pointing at now, and it's got a second one. And the more bends we've got, the more degrees of freedom this has. The more mobile this valve is on the end of here. For example, at this first bend on this right-hand picture, that pipe is quite stiff vertically along its own axis.
Yeah.
Okay, so it's not going to have much vertical vibration at that point. Whereas at this free end, it now can have vertical motion and horizontal motion. It can move in all directions on these free ends. And the same with this other one. The more bends, the Energy Institute assessment doesn't take that into account, how many bends it's got, although I think it should do, because it definitely has a large effect on it. But what the Energy Institute lets us do is calculate this likelihood of failure factor, and it uses just 6 parameters. So this is our small bore connection.
Yeah.
It's our valve arrangement on a pipe welded to a main line. So the main line wall thickness has an effect. The thicker, the better. The type of fitting, I mentioned a welderlet fitting before, that's a common one. That would have a score of 0.7. You have a score for each of these 6 factors, and then you average those out at the end, basically.
Right.
So the fitting type, some have a better fatigue endurance than others. Okay, the weld geometry is different and the fatigue performance is different. Then the branch diameter, the wider the better. The number and size of valves is important. Basically the mass that's supported on this cantilever.
Yeah.
And the overall length. Now actually a lot of these parameters, the length, the mass, the diameter, and the thickness of that parent pipe, all of those same factors are the same factors that alter the natural frequency of that small bore connection.
Yeah.
If it's very long with a big mass, a small diameter, and a flexible connection onto a pipe because it's thin walled, it's going to have a low natural frequency.
Yeah.
That will give it our high likelihood of failure factor, and it will give us a low natural frequency. And that's why most of the problem vibrations on small bore connections tend to be low frequency ones, because the low frequency ones are the ones with the poor geometry, which make them vulnerable. It's exactly the same effects.
Yeah.
The other effect that you have to consider is the location of where that small bore connection is, that welded connection point. Whereabouts is it on a main line? If it's very, very close to a fixed support, we could assume the main line pipe will not vibrate at that point.
Yeah.
So if you like, the small bore has been protected because we've stopped the main line from vibrating. Whereas if it's close to either a valve or a bend, which are sources of turbulence for the flow through the pipe, then there's more likely to be turbulent energy. So it's more likely to have flow-induced vibration at those points. So, so we take those 6 effects, and that will give us our score. So that's just how it's calculated for a small bore connection.
Yeah.
The next of the 6 is this is the 4th one I've got here on my list. So these are small bore connection braces that are ineffective. So on this left-hand picture here, we can see.
Could you zoom in maybe a little bit?
Yeah, I can zoom in on that. So what we can see is we've got a small bore connection with some valves, and it's always, the solutions are always the same. We always want to stop the valves moving because that's where all the mass is, and that's where all the energy is in the system. So if we brace it, we always have to brace to the valve, and we always want to tie it back to the parent pipe, the pipe that it's welded to. Someone's gone to a lot of trouble on this picture to have a clamp-on brace solution here. It clamps onto the main line, and it's got an arm that tries to connect lower down. You can see what they're trying to do. They're trying to protect the welds around that where the weld failures are going to be in there, that welderette fitting.
Yeah, like bending at that location.
Yeah, they're thinking, I'll try and stop it moving at that point because that'll keep the stresses low in those welds, but it won't. If this small bore is vibrating, the energy of these valves vibrating will transfer down this small bore connection and into those welds still.
Yeah.
But also, if you are going to clamp it, it's got to be effective in all directions, in all planes. So for side to side, for vertical, even like all sort of X, Y, and Z planes of movement.
Right.
It's got to work in all of them. This other picture you can see here, it looks a bit pathetic. It's got a brace that's got bends in it. I can't show you my pointer at the same time. I'm going to say, I'll just put the pointer on. It's got a U-bolt connection onto the small bore. It's got a U-bolt connection onto this. I call it a main line. It's quite a small diameter.
Yeah.
But it's trying to stop this valve from moving.
Okay, so the vertical red and horizontal red sections, those are the clamps.
Yeah, so someone's designed those, and just like I said, if a small bore connection has got bends in, it makes it more flexible. It's the same for bracing.
Yeah.
If it's got bends in, it's more flexible. What we want to see here is a diagonal straight line.
Yeah.
Always diagonal. Whenever I see any bracing, I'm always looking for diagonals. If this valve tries to move vertically now, it's got to change the length of this yellow strut that I've drawn on. It's got to load it in tension and compression, whereas on their design, it's just got to load it in bending and a bit of rotation on this U-bolt. So we always want to have that these diagonals to give it high stiffness, but even that wouldn't work in all directions. For side to side, like in and out of the screen, that direction, it's doing nothing. So it's got to. So that's an example of one. Someone's fitted it, but it's going to make no difference.
Right. Yeah.
As a rule of thumb, we want our brace to be 10 times stiffer than the small bore connection is on its own without the brace.
Yeah.
Which means it normally has to look quite over-engineered to be effective.
Yeah, exactly. Yeah.
Another one we see quite commonly, I can zoom in on this one as well. You might have seen these on your own site. So it's got a welded flat bar gusset plate welded to the small bore pipe and welded to the main line pipe.
Right.
So it's not doing everything I said before. It's not supporting the valve, and it's not supporting it in all planes. If this valve tries to move vertically up and down, that gusset plate's not going to stop it.
Yeah.
What it is going to do, it's going to add additional welds that have now been welded to our pipe, which are likely to be highly stressed because this gusset plate is, because of the leverage effect of this mass vibrating, we could have more highly stressed welds, and it's just as likely to have a crack at those welds instead of the original welds. You can still have gusset plates. They're not totally they're not best practice now, but I've done something crazy. I'm going to say, I knew that was bound to happen. Hang on, I'll get you back. Sorry. Sorry, just bear with me.
No worries. Take a second.
There we go.
There we go. Yeah.
Back in the room. If you have got a welded gusset plate like this one, you need to use a reinforcing plate. Okay, that's what the guidelines will tell us, to reduce the stresses in those welds to stop those from cracking. But it's still not effective in all planes. It just means it won't be damaging if you put that reinforcing plate in. The best way to do this, like always, is to support that valve back to the parent pipe.
Right.
The main line. Okay, and then the next one, which I see quite a few of as well, quite a common one. I
just to be sure, like Neil, we're advancing rapidly in time, as always.
Okay, well, that's good.
So, but no worries. Like, I, it's really interesting to discuss these pictures. You know, we have a few slides with pictures. Let's focus on these and then start wrapping up. I think.
Okay. Well, this is an example of a small bore connection it's near to the ground. They've put a bend in it because there's not enough space for it to be a straight line. So they've put a bend in it there. And because they want to stop it vibrating, they've fixed it to the ground, thinking, well, what can be better to stop that from vibrating?
Like an anchor
if the
point.
main line is still vibrating, this is now basically trying to act like a fixed support for our main line. And it will put high stresses at these welded points. The picture on the right is just the same. It's just a different example of one of those. We've got a small bore connection that's actually, I should have.
It's mounted to an I-frame bar.
Yeah. They've put this extra steel bracket in that's circled in yellow on here. So the free end of our small bore connection is now attached to that fixed point, which is attached to a horizontal support beam. But again, if the main line is vibrating and the fixed one end of the small bore connection, that differential movement will cause high stresses in these welds. At that weld and that fitting. Okay, just a couple more slides then, and let me just.
So just like it is an interesting point. Just like, how would you solve it? I mean, obviously, like for example, if you go one slide back, Neil, and then the left picture, you want to.
This left-hand picture.
Yeah,
what we want to do is
or something, I guess, right?
We want a brace that attaches to these valves and ties it to that pipe, the same pipe that the small bore connection is welded to. So you'd have a connection across here. On this other one, I suppose it's difficult because that beam is in the way. That is a very difficult one.
But key is
for that one, it would be better to reorientate that small bore connection and then fit a brace. But I'll show you that other solution in a second, which is, this is just to make the point that the vibration that's affecting the small bore connection is caused by the vibration of the main line. And so if the main line isn't well supported, like in this case here, so this is a sliding support or a rest support, but due to thermal expansion, the main line is lifted off, creating a gap. Then you might think your main line is supported every 8 meters. But if you've got one of these gaps up here, it might be now 16 meters, or it might be 24 meters. You might have a whole section of pipe that's really unsupported, which on paper looks good because you've got to support every 8 meters, but in practice, it's not good. So you do need to do that visual assessment to make sure your supports are effective. Another problem that can affect it is where you've got U-bolts with missing liners or clamps with missing liners. It's the same thing. It's the same principle. Make sure your existing supports are as effective as they should be, and then you might also need to add additional ones. I'll just quickly move on to show you the solution, because you mentioned before about how can you do it, and this is something I was involved in, which the idea was to make a generic solution that could be used for all small bore connections that you could specify with 2 dimensions. So you can imagine that all these parts in grey are stainless steel fittings are stainless steel castings, stainless steel fasteners, stainless steel tubing. It's all corrosion resistant. And it's basically a clamp. It clamps onto a flange on a valve, and it clamps onto the outside of our main line. To specify it, you just need to know those two diameters, and you'll get those from your isometric drawing. You don't have to go to site or do any measurements. You just need to look on your drawing and say, oh, that's a 1.5 inch, 300-pound valve, so it'll have a certain fixed diameter of flange, and that's a 12-inch pipe, and they all have the same outside diameter. It comes in different configurations. It's the same product, but it can be used to attach to different configurations of small bore.
Right.
Irrespective of how many bends you've got in there, it's all down to the orientation of the valve compared to the orientation of the main line. That's what's different on these three pictures.
So this is like a universal clamp, and as long as you can make
universal.
it fit on the header, then you should be fine.
Yeah, you basically bolt this onto your valve, and you bolt the split clamp onto your pipe, and these arms aren't fitted at that point, these struts. You then align these fittings by eye as best you can. You measure the distance between them with a tape measure, and you cut that tube to length on site, and it's guaranteed to fit then because you've just cut it to length. And you can have these, they come in a 2-arm version, a 3-arm version, or as shown here, the 4-arm version. The next picture I've got for you actually is an example of a 3-arm version of this.
All right, yeah.
You can see on one side of this, they've got a clamp onto the pipe, and on the other side, they've got a clamp onto a flange, because you have to sort of work with what's available at the space. So on this one, you need 3 dimensions. You'd need to know that flange diameter, the pipe size, and the flange on the small bore connection. But that would just be fitted on site by a fitter. It's supplied as a kit with a set of instructions. You fit it yourself. So it's just to make the point, it's not always that difficult. Even if the geometry is complex, solutions exist. This is one solution. You might find others similar, but solutions exist that do exactly what the Energy Institute says, which is to tie this mass, the valve on our small bore connection, back to that parent pipe.
Nice. Thanks for showing. So just one question to wrap things up. I mean, we're a little over time, so we'll have to start wrapping things up. Neil, no worries. I mean, there's interesting images to discuss. Like I can imagine that. Well, coming from a pipe stress background, there's always a bit of a discussion about gaps in pipe supports, right? What is acceptable, what during installation, etc. How do you deal with that from an analysis point of view? I can imagine that since the amplitudes of these small bore connections, the vibrations can be really small. I mean, not even visible to the naked eye. You just mentioned that the clamps. Have to be, or the braces have to be really stiff, and that any flexibility in, I don't know, even screws or nut bolts and all those joints are, make it very ineffective. What is your take on that? I mean, it must be difficult.
You're quite right. You do need a high level of stiffness, especially if we're aiming to have our brace 10 times stiffer than the small bore connection.
Yeah,
that is for the same applied load to it. That would cause our small bore connection to move by 1 millimeter. We want our bracing to move by just 1/10 of a millimeter. So to get that really high stiffness, you do need something that's well engineered and well attached and maintained. That easy brace example that you can see here, that's got it uses Nordlock washers. I don't know if you've heard of those. It's an anti-vibration washer on every single fixing.
Right. Yeah, exactly. Yeah, you need to take those type of things into account.
I think you'll be able to see them on this picture. It's not enough detail, but it's because if it needs bracing for the integrity of that small bore connection, then you need to make sure it doesn't vibrate and fall off, a month after you fitted it. It's got to be a permanent solution.
Yeah. All right. Well, thanks, Neil, for sharing your insights on these, and especially on these small bore connections. Like I've been involved with vibrating piping systems, but those were like the header type vibrations due to water hammer, etc. So this was very insightful for me, at least, about how to deal with those small bore connections. So just for everybody out there listening, so thanks for joining today. And if this is a topic you would like to know more about, as I mentioned in the beginning, Neil will give a course called Pipework Vibration Training, which covers all of this and much more in greater detail. So the link is in the in the description. Make sure to review it if that is relevant to you and your team. Thanks for joining, Neil. Thanks again for making the time. Have a great day, and we'll hope to connect soon.
Yeah, thank you, Luuk, and it's always a pleasure. And thank you to everyone who's signed in online to watch it.
All right. Likewise. Have a great day. Bye bye.
See you next time. Bye.